does the handedness changes when the relative retardation is modified?
Now, let us go back and then see this slide. See, you have this expression tan 2 beta equal to 2 ax ay divided by ax squared minus ay squared into cos delta. So, when delta changes, you can easily see that beta also changes. In addition, what you find is when I have delta for different ranges 0 to pi by 2 or delta equal to pi by 2, pi by 2 between pi by 2 and pi, what you find is when you go and actually plot the trace of the light ellipse, you find the rotation is different, and that is what is illustrated in this series of graphs. So, when you have delta lying between 0 to pi by 2, I have to go and actually plot the resultant vector, the trace of the light vector when I do it as a function of time. If I see different instances of time, the vector will change like this. So, that is what is indicated by the handedness. So, when I have from 0 to pi by 2, I have it like this, but if I go to the other extreme pi to 3 pi by 2, the handedness changes. Azimuth change you can directly understand from this expression, but for getting the handedness you need to really plot the trace of the light ellipse. You have to do it for at least 2 steps, so that you know the direction, whether it is anti-clockwise or clockwise. I need to do it for 2 different instances of time, and that is what is summarized here. So, if you see one after another, it will go in a sequence. When you have delta equal to pi by 2, the reference axis become the axis of the ellipse, then it gets tilted like this, then the handedness changes, then it becomes horizontal, then you have this tilted like this. And we also looked at the special case in addition to whatever the relative retardation, if Ax equal to Ay, what we saw was you do not have an ellipse, but you have a circle, and 2 types of relative retardations possible, delta equal to pi by 2 or delta equal to 3 pi by 2. You have one type of handedness when delta equal to pi by 2, you have another handedness when you have delta equal to 3 pi by 2. See, if you look at in conventional photoelasticity, handedness has not played a very significant role. On the other hand, when you come to digital photoelasticity, the handedness has played a very important role. In fact, we have looked at 10-step phase shifting technique, which has first 4 steps as plane polariscope arrangement to get isoclinics. The second set of optical arrangements are 6 in number, they are arranged in a circular polariscope, and if you look at very closely in the optical arrangement, the first 4 arrangements will have a left circularly polarized light impinging on the model. The last 2 arrangement you will have right circularly polarized light impinging on the model. This made a difference to accommodate quarter wave plate error better. See, whatever you say as a quarter wave plate, it is matched for a particular wavelength, and if that wavelength is different from your illumination source, it will not behave like a quarter wave plate, and in many instances we may have to live with a mismatched quarter wave plate, and mismatched quarter wave plates did not play that damaging effect in the case of conventional photoelasticity, where we have also discussed that crossed quarter wave plate arrangements are preferred orientations. That automatically took care of minimizing the error, but the moment you go for intensity processing in digital photoelasticity, people found by changing the handedness of the incident light ellipse, the influence of mismatch of quarter wave plate could be minimized. It cannot be eliminated, but it can be minimized. So, what you find is Though in conventional photoelasticity, handedness has not played a significant role, it has played a very useful role in digital photoelasticity. I suppose you got some idea of why we discuss handedness, how handedness come into place and where it is useful. So, you need to know the complete story behind it.
Fringe ordering is one of the important aspect in the photoelasticity as we came from this course. Just we want to know what additional precautions we have to take so that we don't miss the correct ordering and do, or is there any way to validate what we do?
See, I have said correctly that fringe ordering is one of the crucial steps in photoelasticity. Not only in photoelasticity, in all the optical methods, fringe ordering is very important. Since we focused on photoelasticity, we will go and discuss what ways you can salvage your problem. It depends on the problem that you handle and the kind of facilities that you have access to. See, suppose you have a situation where I can repeat the experiment by changing the load, then I could get a picture like this. So, even if you have made some numbering of fringes, those numberings could be checked, because when I change the load, I am able to look at that fringe order vanishes here. So, it is a sink, and fringe order does not vanish, the fringes become denser and denser. So, it is not a sink, but something else. And if you are also in a position to go and look at a plane polariscope, I could verify that all isoclinics passes through this point. So, it depends whether you are given a photograph. If you are given a black and white photograph, it is very difficult to do. You do not have to feel disheartened that you are unable to order a fringe given a photograph. It is not possible. On the other hand, if somebody gives you a color isochromatics, a single photograph, and if you refer to the color code, there is some way to find out the ordering of fringes. The best one is you have the model on hand and you are also able to have access to the polariscope, and then and there you verify whether the labeling of fringes is correct. That is the most simplest case which you can do by varying the load, by rotating the polarizer analyzer combination. So, you have a via media to do that, but in complex problems fringe ordering is tricky. You have to accept that fact. And by looking at several problems, say for example, if I take a internally pressurized cylinder, that is typically a Lamis problem. In a Lamis problem, you all know that inner boundary is loaded to the maximum. So, you will have maximum fringe order in the inner boundary. What is the fringe order on the outer boundary? It is a very special case, because the outer boundary, it is not 0, because you have looked at a circular disc under diametric compression where you have outer boundary is 0. You cannot simply extrapolate that kind of understanding, a wrong understanding, to a generic problem. Say, I have also mentioned there are general rules and exceptions. On the circular disc, the boundary is 0 was an exception. You have a beam under 4-point bending, you have a neutral axis, 0th fringe order is like an axis. And we also saw the problem of ring under diametric compression, where you had fringes on the outer boundary and you had only 1, 2, 3, 4 points on the outer boundary and 4 points on the inner boundary where fringe order was 0. So, we also saw a counter example. See, one danger what is possible is when I have a free surface, you tempt to think fringe order is 0. That was the case in the case of a circular disc, which is a special case. We also saw the beam under 4-point bending. You also had tops and bottom surfaces as free, but they had fringes depending on what is the load that you have applied. So, on internally pressurized cylinder also, on the outer boundary, finding out fringe order is difficult. So, you have to look at a color code. In fact, people have solved that kind of a problem by finding out the interfringe distance and developed a methodology how to order a fringe. So, if somebody gives you a photograph alone, if you are unable to find out the fringe order, do not feel disillusioned. You need additional data. At least with your training, you should ask for additional data. That is what the training is, because you are definitely solving very complex problems in experimental mechanics. You are not talking about simple problems with simple loading. So, in complex problem situations, you may have to use different strategies. So, you are able to look at the isoclinic fringe field, isochromatic fringe field, or principles of solid mechanics, or use color code, or in the worst case you also go and post process your finite element result and then plot the fringe contours. From there also you can verify whether your fringe ordering is correct. So, you have to take multiple paths. When the problem is complex, you will also have to be ready to spend time and money, and fringe ordering is crucial, and that is where you have modern techniques like digital photoelasticity, which simplifies to a greater extent on identifying the fringe order. But even there I caution, many of these software modules are developed based on certain example problems. If your practical problem falls within that domain of complexity, then that software will work. If you go beyond that level of complexity, the software may not have a module to look at it. So, it is always better that you get trained, even though you use digital photoelasticity for fringe ordering, learn the conventional methodologies on how to identify the fringe order. So, that will complement your result from digital photoelastic analysis. You can verify, you need to know whether the software has worked correctly for the class of problems that you are handling with.
So, what are the fringe thinning methods and what are the various algorithms involved in it?
See, fringe thinning methods are used in the early development of digital photoelasticity, where people wanted to mimic what you have been doing it in conventional photoelasticity with the help of computers and scanners. That you will have to understand. Whether fringe thinning methods are essential these days for solving a problem, it depends on what question that you want to get. In certain class of problems it can be useful, in certain other class of problems you can go for phase shifting techniques and find out the fringe order. And if you look at fringe thinning methods, they can be broadly classified into two categories. You have what are known as binary based methods, and you have intensity based methods. In binary based methods, if you look at the genesis, one of the earliest image processing application was on optical character recognition. So, the challenge was, when somebody writes, you should have the computer to recognize, yes, he has written the letter A, letter B, letter C, and depending on each one's handwriting, the shape may slightly differ, but there would be certain connectivity that would decide whether it is letter A or O, if you take two extremes. So, in those cases they essentially looked at the characters as a binary image, and they had developed algorithm to look at the connectivity and also look at the skeleton. So, people thought, why not this algorithm could be employed for fringe thinning. That was the first step. It slightly crude in its approach, and the philosophy in that was recognize the fringe area as a binary image, and how to get this fringe area. We also saw that it can be done by a simple thresholding process. Then you use the method of optical character recognition and strip these boundary pixels progressively. It cannot be done in one step. because you have thin fringes and thick fringes, you have to keep removing the boundary pixels. And how to identify that this is a boundary pixel and remove, we saw the algorithm of Chen and Taylor. You may have a question how he arrived at that kind of criteria that this is the boundary pixel, if the pixels are arranged in this fashion, if we have fringe pixel, non fringe pixel, and if this satisfies this condition, remove it or retain. These conditions are obtained by trial and error. If you really look at, they are not directly apparent. You get some idea, implement it, then improve upon it, and you take some time to develop that algorithm and apply it to a class of problems, then improve your performance of the algorithm. You get the basic idea is strip the outer pixels. So, that is what is done in binary based algorithms. On the other hand, when you go to intensity based methods, you retain the fringe field as grayscale images, and from your analytical development, what was the fringe point? The fringe point was the point of minimum intensity. So, if I have intensity recording, then I can pick out those minimum intensity points and they form the fringe skeleton. Now, the question comes whether it is a global minimum or local minimum. See, when you go to any experimental arrangement, you have a light source which is a diffuse light source. So, light may not be uniform, even though for your eye it looks uniform. If you put a CCD camera and measure it, there may be small variations. And similarly, when you have the optical elements, when you have the model, uniformity may not be guaranteed on the entire area. So, you cannot say that a particular value of intensity will be the fringe skeleton globally. You will have to go for a local minimum. And here again there are several methods. You have mask based methods as well as global methods. In fact, in the class I did not discuss about mask based methods. I directly discussed the global methods. And if you look at mask based methods, they would take a mask of a particular size, and within that mask they will try to find out how to identify the minimum intensity. It will find out the minimum intensity within that mask, and you have many algorithms for that. In fact, the literature has about 50 to 60 publications on this. And what we saw was, in the global methods, we took two simple examples. One is vertical fringes and horizontal fringes. Suppose I have horizontal fringes like in a beam, I can develop a scanning methodology which is perpendicular to the fringe areas. It will automatically pick out the minimum intensity. So, when you join them, you will get a fringe skeleton. Suppose I have a complex fringe pattern like this, which you see at the tip of a crack. The fringes are very sharp near the tip of the crack and they are very broad here. I cannot take a horizontal scan, I cannot take a vertical scan and pick out the skeleton. What I need to do is, I need to take tangents and then draw the normals. So, I should scan for this portion only along this direction to pick out this point. For picking out this point, my scanning direction should be altered. So, the scanning direction changes as a function of the curvature of the fringe, which is very complex. Conceptually, picking out minimum intensity point was simple, and the algorithm was simple and straightforward when you had horizontal fringes or vertical fringes. But when I have a complex fringe, you may even think, let us give up, let us go and use mask based methods. That kind of thinking is possible, but what we found was a finite number of orthogonal scans and clever use of logical operators have simplified the whole process. Even when I have an arbitrary geometry, it is enough I scan the image horizontally, I scan the image vertically. The scanning direction is simple and straightforward. The implementation is also very simple, and you take a logical OR of these two, you get a fringe skeleton completely, but this will have noise. And you have another set of orthogonal scans, 45 degree scan and 135 degree scan. Here again, when I do this, I get the fringe skeleton complete, but noise is in a different orientation, fortunately. And when I take a AND of these two results, I get the fringe skeleton totally free of noise, and this took us almost a year to develop. It was not as it takes me 5 minutes to explain, and I will also show you the results. If you see the results, you will know, and this is what is shown. So, I have a 0 degree or 90 degree result. Individually, when you look at, some portions are not having fringe skeleton, and you have those fringe skeletons available in the other orthogonal scan. And when I take the OR of this, I get fringe skeleton as well as noise. Is the idea clear? Are you able to see that individual scan does not give you complete fringe skeleton? Some portions are missed in this, some portions are missed in this. In fact, many portions are missed in this because the fringes are primarily vertical. So, when I have a vertical scan, it does not pick out those portions. When it is become tangential, you do not get the result. And when you look at the other set of orthogonal scans, here also you will find when the direction is tangential to the fringe areas, those areas are missed. When I take a logical OR, either this or this, that is what it will do. See, I essentially have a binary image here. I have black background and white points are the fringe skeletons. That is how it is handled. So, applying the logical OR operation is also straightforward. So, what I see here is I get the complete skeleton plus noise, and now what I do is I have looked at these individual results, I find there is correct result plus some noise, and noise is different. See, when nature wants to reveal something, it also provides you methodology. Suppose you have a case where the noise is same, then I can't take the AND operation and it will do. So, you have to find out what kind of trick works, and when I do the AND operation, I get the fringe skeleton free of noise. And we have later done a work which showed comparison of various fringe thinning methodologies, and we found that this takes 1/10 of the time. And in those days, we were having only a PC XT computer. It used to work very slow. In fact, you can allow a 0 degree scan and go for a cup of coffee and come back. By the time you come back, the computer would have done that 0 degree scan. Now, the whole process is done in a second. So, when in those days when time was at a premium, even the methodologies which reduces the processing time is significant. So, the message here is look for new ideas. See, people have never used logical operators earlier in these occasions. We looked at that logical operators provided this giant leap, and we were able to get very good skeleton. But before we apply this fringe thinning process, you need to do certain pre-processing of the images. And one of the aspects I said is you have to have a time averaging. You take 16 frames or 32 frames and then take an average of this, and then do some kind of a spatial averaging, some kind of histogram equalization. When you do all that, the final fringe skeleton will be of 1 pixel width, and it will also be continuous. And this has application in certain domain now. With phase shifting techniques, fringe thinning methodologies are becoming to a cold store.
Sir, how does the photoelastic strain gauges work?
See, in a photoelastic strain gauge, what you have is I have a polarizer and quarter wave plate. They are shown here separately, but in actual manufacture this will be pasted on the coating itself. You have a separate plastic base which will have the coating with the polarizer and quarter wave plate integrated. And if you look at in circular polariscope, you have what is known as a bright field and dark field. I can have the quarter wave plate parallel as well as crossed. So, when you put it on this, you will see one of those fields when there is a light goes into it and comes back. So, that is the difference. In the case of a normal reflection polariscope arrangement, I have polarizer quarter wave plate here, I have another quarter wave plate and polarizer here. Here I have a control for me to view the bright field or the dark field. In a photoelastic strain gauge, I do not have that control. I would see one of those fields. I think that answers your question.
Sir, in that case, will the thickness of this quarter wave plate and polarizer plate will be sufficient to give the required retardation and to get the enough fringe orders?
See, the polarizer and quarter wave plates are optical elements, they do not provide you retardation. So, your question is whether the quarter wave plate provides you a retardation of 90 degrees for you to get the circularly polarized light, and you have such thin plates available. And even if you look at a polarizer, you have polarizers of various thicknesses available. The quality of polarization may be better in a thicker polarizer, but here in the case of a photoelastic strain gauge, you are not making a very precise measurement. There you are only looking at a pattern, and in those days when these photoelastic strain gauges were developed, they were essentially trying to find out whether you have a uniaxial stress field or a biaxial stress field. The focus was only that. For that kind of a focus, even a reasonable amount of quarter wave plate is good enough for you to reveal the information. So, it depends on what level of accuracy you are really looking at, and it may not be 100% quarter wave plate. And we have also seen even in conventional polariscope, you have a mismatch of quarter wave plate that becomes significant when you go to digital photoelasticity. So, when you are working in conventional polariscope, the quarter wave plate errors are naturally absorbed because you are having crossed positions, and in the case of photoelastic strain gauges, because you are only looking at overall pattern to find out whether it is a uniaxial and biaxial stress field, these whatever the thickness that you come across are reasonably sufficient to give you the pertinent information.
How do we select the suitable gauge length for a given class of problems?
See, in strain gauges we saw we want to measure strain at a point. If I have a magic material which I can take a speck of it, put it at the point of interest and somehow make the measurement, that is well and good. Unfortunately, you do not have that kind of a material. So, I need to take a wire and then make that as a grid, because I need to have some base resistance for me to make the measurement comfortably. So, I essentially have a grid. So, when I have a grid like this, the strain variation over the grid is going to affect my measurement. Suppose I have a uniform stress field, and when I have a uniform strain, when the strain value is constant, the length of the grid element does not matter. So, the gauge length does not play a role. You essentially measure the actual strain, whatever the strain at the point of the center of the grid would be the one which is measured by a longer grid also. Suppose I go to a problem of bending where strain varies linearly over distance, even there the gauge length does not play a role, because the average value of this will match with the strain at the center. And mind you, when I have a strain gauge, I have markings, and what I do is I align the strain gauge at the point of interest. So, what I essentially do is at the point of interest, when the grid lines or whatever the guidelines on the carrier pattern are aligned, I say that this is the strain I measure. And when you are looking at the gauge length, when it is uniform or varying linearly, the strain measured at the point of center is same as what you measure on the strain gauge. Suppose I have a sharp variation, I am not having a uniform or linearly varying strain picture, then what I sense on the gauge length would be different than the peak strain. See, this is the point of interest where I would interpret the strain result to be. For this point, because of sharp variation, you have a very high value of strain, which is not same as the average strain which is measured by the actual strain gauge. Suppose I keep reducing the width of the gauge, that is essentially the length, then I will make it smaller and smaller, and I can approach this peak strain very closely. So, it is actually dictated by the gradient of the strain variation. And how do you do that? You have a thumb rule available. The thumb rule is, we have seen two problems. One is a gear teeth, I want to find out the stress concentration region, this value of strain, it is very, very small, and thumb rule is the gauge length should be no greater than 0.1 times the radius of a hole, fillet or notch. This is only a recommendation. If you are able to match it, well and good. And you have stress concentration in the case of a plate with a hole, and I also said instead of pasting it on this surface, paste it in the inner surface of the hole. And we have also noted it is always prudent to go for a 3 millimeter gauge length for general purpose. When I go for shorter gauge length, stability becomes a problem, range of strain measurement becomes a problem, bonding is a problem, soldering and heat dissipation, all these are issues. So, if you address them correctly, then you can choose the smaller gauge length for problems where they really demand. As a thumb rule, for metals, go for a 3 millimeter gauge length. Only when I work on concrete, because it is heterogeneous, you want some kind of averaging, you go for longer gauge lengths. So, selection of gauge length is closely related to the problem on hand, and what is the strain variation that you are anticipating. So, this is where you find optical techniques are far better, because gauge length is 0 there, but strain gauge has an advantage because of its versatility. It can be applied for a variety of problems. Even though I make approximations, I get some answers for my design.
While installing the strain gauge, why you are rubbing in 45 degrees by using emery paper?
See, the essential requirement for surface upgrading is to prepare the surface so that I have a surface roughness of a desired magnitude, so that the strain gauge can be bonded comfortably. And what we looked at was, in the case of aluminum, use of a 320 grit followed by 400 grit is recommended, and for steels you need to select 220 grit followed by 320 grit. The next stage is, how do I go and really do this process? You are actually doing a wet lapping. You have a conditioner, and then you need to do the wet lapping of the surface, and the specimen which I have taken is very small. I also need to have some area for me to do the rubbing action. So, if I do it, I need two orthogonal directions, because it is very thin and narrow. If I take at 45 degrees, I will have equal amount of rubbing length possible. And here I also caution that you are not testing your muscle power, you are only supposed to do the wet lapping 12 strokes this way and 12 strokes this way, that will provide you the necessary roughness for strain gauge bonding, and depends on, I need only orthogonal directions. Here, because it is narrow, I go for 45 degrees.
In determination of boundary stresses, what difference does it make when you paste the tensile specimen parallel to the model or perpendicular to the model?
See, let me put it this way, we are not pasting the tensile specimen on the boundary, first thing, and the other one is we are not finding out the boundary stresses, we are only finding out the sign of the boundary stresses, we are not evaluating the magnitude here. And you have to understand, in all the retardation discussion which we have had, you have reference axis at the point of interest, and these reference axes coincide with the principal stress directions at the point of interest, and you add or subtract retardation only along those axes, and we are looking at a free surface. So, when you are looking at a free surface, at any point on the free surface, tangent on the boundary and perpendicular direction on the boundary are the reference axis. So, you need to add or subtract retardation along those reference axes. When I keep a tensile specimen tangential to the boundary, you are adding retardation in the horizontal direction or tangent to the point of interest, and when I keep it vertical, I add retardation in the direction perpendicular to it. You are only seeing the fringe order as sigma 1 minus sigma 2, and if sigma 1 minus sigma 2 increases or decreases, you will see that by a change in color, because the variation is very small, only a color change can give you whether sigma 1 minus sigma 2 increases or decreases. And what we saw in the class, suppose I keep the model tangential, and if you find the fringe order increases, then the boundary stress is positive, because I have already retardation in this direction, I add in addition to that another retardation. If the original one was positive, because when I have a tension specimen, I am applying a positive retardation. If the original one was positive, it gets added to that when I keep it tangential. Suppose for the same point I keep it vertical, that becomes sigma 1 minus sigma 1. So, you have to look at what way sigma 1 minus sigma 2 changes. You will actually get a complementary answer here. If I say in the case of keeping it tangential with the fringe order increases, I say positive. If I keep it perpendicular, when the fringe order increases, the boundary stress will be negative. When it is negative, sigma 1 minus sigma 2 will become sigma 1 plus sigma 2. So, the fringe order will increase, and here you are only keeping this specimen close to the model, you are not attaching it, it is like a external compensator.